It's went so much smoother last year. We'll try.
Let me use the mic, I think.
The mic is out of battery, so if you would please plug it back in, that would be great. I realized the charger wasn't plugged in. That's why it was out of batteries. But now the charger is plugged in. So if you get it oriented right, the red light will come on. Okay. Thank you, everybody, for your patience this year as we work through our technical challenges. Okay, what is a computer science presentation if the professor cannot work the slide projector? I'm not sure, but let's continue. I'm Tim Henderson, along with my colleagues here, Sush, Avi, and Abe. We're going to talk about multi-architecture testing at Google. This is a big project that we've been working on for 3 years now to do. So we're going to give you a snapshot in time view of it. So it's going to go a little bit fast, be a little high level, but hopefully you'll get a sense of the complexity for us and what we're doing. So what is multi-architecture testing? Well, at Google, we've recognized that Moore's law has ended. Scaling limits on transistor sizes, as everybody knows. We've hit power law walls, all the things that were causing hardware to get faster and faster and faster has sort of stopped. And so now we're in the time of domain-specific chips, whether it's an accelerator or something else that you're doing. So we're no longer seeing scaling happening for general purpose compute. The domain-specific chips are on the rise. And we're also having an increased desire to have a lower power general purpose compute. And so for all of these reasons, Google, along with the rest of the industry, is deploying R on the server side. This is a screenshot of a public blog post from the cloud division about the product that you can buy from Google Cloud for running your virtual machine workloads on the ARM machines today. So you can go there, you can spin it up. But this is actually not about the cloud. It's buried in this article, but the article talks about how we're running production workloads that are non-cloud also on the ARM machines. And that's what this presentation is really about, because Google runs most of the majority of the services that it runs that are used by the consumer, not on cloud services, but on the thing that runs the cloud services. So we're going to talk about how we are going to qualify software for this new world where we're deploying software either on x86 or on ARM machines, and often the developer is not making that as a conscious choice. Their software should be ready at any time to deploy on whichever machine is available, and to do it so that whatever is cheap is what it's going to get deployed on. So there are a bunch of challenges with doing this sort of qualification of software for another architecture at a large scale. First, we need to make sure that we can actually test all of our software on the new architecture. So we need to at least be able to do a one-time qualification. Does it compile? Does it build? Do we have architecture-specific code that needs to be ported? All of this is sort of like a one-time qualification activity. But then after you've ported the software, you've replaced the compiler intrinsics, you've rewritten your assembly code, we actually need to continuously requalify as people make changes to make sure there's no backsliding, that the software continues to work on both architectures. So we can't just do it once, but we can't just always do it twice, because that would double the testing cost, or you run it all the tests twice just to make sure that there's no architectural skew, which is sort of a rare event. It's not super common. Not a lot of software is really that sensitive to what architecture it's on, especially if it's in a high-level language, but some software is. And so in order to qualify a new binary for the new architecture, the developer, if they actually want it to get used, is also going to have to change some small amount of their configuration. to put in the right, sort of compiler flags and this and that. And we need to make that easy because that's human effort that they have to do. So we're sort of scaling in 2 dimensions. We're going to scale in machine effort, we're going to scale in human effort. So we'll talk about machines first. This is a picture that I drew with a little picture drawing tool that I made based off of what our actual testing costs look like as a curve over time. And it's bumpy because periodically we hit these moments where we hit a resource crunch. Leadership is like, make testing cheaper, make building cheaper, and a bunch of people go off and they do various projects to like reduce testing costs. And then what happens next is here-ish, they declare success. We've made testing costs sustainable. Good job. Everybody applauds, they pat themselves on the back, they get an award for saving so much money, and then they go back to other things. And then testing costs increase again. And so this has happened a number of times now. So we know this pattern of in and out on the resource costs. So at least we know it on the lower levels, maybe the executives got the message in. But we're thinking about how this cost goes up and down over time, but is generally sort of creeping up in an exponential pattern. And so you can model that, with a curve fit, and it looks something like that over the long term. And if you just add ARM on top of it, you just make a one-time bump that doubles it, and then you continue to go up that curve. Except now it's translated up higher. And so this is the situation we want to avoid. So that's our first problem. Our second problem is configuration. So this is the number of projects, CI projects we have that run on the primary CI system, which is called TAP, which most of us here work on from Google. And if they're not working on it now, they worked on it in the past. And the red line is the number of CI projects. The blue dotted line is the number of individual basal targets that are test suites. So lots and lots of targets, lots and lots of projects. We had a one-time human intervention that deleted a lot of auto-generated test suites that were testing various things. And right now, in 2025, we have approximately 3 or 4 CI projects per human developer, which is quite a lot of CI projects. And so if you were thinking about having developers make manual changes to the configuration, even if it's a very simple change, they're going to have to make it at least 4 times. So you might be asking, why are there so many CI projects? And the answer is they're really easy to make. They're not necessarily easy to maintain at scale if you've got tons of them, but setting them up is very simple, especially in comparison to what people had to do before there was TAP, which automated it all away from people. So really, this is the minimal configuration you need. You have a name for your project. That's like the ID. That's how you'll find it. Very minimal config, or none at all, such as frequency, which is an optional thing. Otherwise, we just run it as frequently as possible. So most people don't set that. Some basal flags to use if you need to customize the flags. Once again, completely optional. You don't need to set it. We'll just run with the default flags, and that's actually what we would like you to do because it's more efficient if everybody uses the same compiler flags. And then finally, which targets to run, which we represent as basal query patterns. And so that gives us a list of test and binary targets that TAP's going to be able to run. So it's like, really, just 2 required things, and you're off to the races. You put it in a file, and you're done. And often, it's super easy to make, and people make lots of them. And we also have tooling that makes them on behalf of people when they're doing certain things. So sort of in a more formal level, I like to think of it like this. Tests are grouped into projects, and this forms a bipartite graph, which means you have a graph with 2 node colors and the colors never link directly together. So on the blue side, you have projects, and on the orange side, you have targets. And you can have a project that includes targets that are in another project, and you can have targets that are in multiple projects. So it sort of can get a little bit dense at times. And as it gets denser and denser, it's actually hard for us to store it. It changes over time. So any commit that people make can change the nature of this graph, and we have to keep processing at all times. So this makes, this is the reason why TAP is difficult for us, is because actually tracking the configuration changes at the speed that we have to track it is very data intensive. And that's why we spent actually a lot of time on TAP just working on this problem right here. When you are trying to make a release in release software, typically multiple TAP projects participate. You're testing different things, maybe with some different configurations. And so you typically sort of add up the status from each project into a single release. So in this example, release 1 is the combination of project 1 and project 3, and they are green because all the targets in those projects are green. Release project 2 is red because the CI project 2 is red. It's a little bit complicated, it's a multi-level structure, but that's how it sort of works together. So now I show you a real example of what the configuration is that people have to work with. So there's a horrible configuration file that people write in. It's called a blueprint. It has a custom configuration language. Don't worry about the syntax, but that says sort of the minimal amount of code that you would typically write. There. So we've got the name, which is example, the build flags, compilation mode equals opt, a target pattern, and then you say, okay, here's my continuous test. It uses this buildable unit. Here's my buildable units, and there's a number of ways you can structure this file, so it's slightly simpler, but it looks like this generally. So when we go to add ARM to these files, which are in this format, it actually requires a lot of manual changes. So if we did nothing, we would minimally need to add some things like --CPU equals ARM. Okay, now we're going to run on a great. We might have to exclude some tests. We would do that by adding exclusions or adding target filters, which you can do as well. Then we need to add another continuous test. That's all good. So because of hooking your CI projects up to the release automation is a bit of effort, you need to make many changes later on in the file to like add everything together. So not only you're creating the CI projects, but then you're adding them in multiple places throughout the release configuration. So this is, something we've done to ourselves with our configuration format. But if we have to change every CI project at Google and we have 300, 400,000 of them, this is a problem we have to solve. So we're going to make 2 big changes. We're going to automatically configure all those TAP projects so that nobody has to touch the blueprint. So that's our first win. And our second win is we're changing the scheduling algorithms in order to conserve machine resources by load balancing between x86 and ARM. And then sort of only at the final step, making sure that we have enough qualification done to do release for the risk profile that the release project is. So that saves actually a lot of resources because typically releases go to prod less frequently than the main CI. So that's the intuition there. So all of those changes before, it was like 15 different things that you had to do. We've squished it down to 1, which is something that the user actually isn't going to make themselves. They're just going to approve it. So we'll send them a change to review. They'll look at it. They'll look at the message. We'll tell them why it's safe and also what it will do for them, and they will approve it. So, yes, time check. Let's see. Martin, what time is the presentation slot?
5 more minutes.
5 more minutes. I'm going to breeze through this. by going like that. That was how the machines got configured. The configuration was done automatically. You saw it very fast. But I'm going to hand it over to Sush now to talk about the architecture alert schedule.
Hi. So we have all these projects set up now, and like Tim was saying, we can just run them twice, and that is what we do now, but we just run them twice once a day because we just cannot afford to run them twice all the time. And so when you consider all the targets in a project, you have a bunch that can only run on like the version they run on now, which is all of the x86 machines. There's an overlapping subset of what targets can run on the ARM machines, but these are not guaranteed to always look like this. Projects can have targets that only run on one, only run on the other, or some intersection of both. And what Tab does now is this, right? So we'll run all of the things on the x86 bucket one time, and then we'll run everything in the ARM bucket one time, and then we'll try to merge the results. But we've been doing a lot of work in this area, which is that because targets can indicate which machines they're compatible with, and because Bazel is like capable of being able to tell us, oh, hey, here's these targets that are only compatible with one or the other because we've spent all this time building a centralized configuration system, we can be much smarter about using some resource awareness in terms of which machines are actually occupied, how heavily are they occupied, and do we have any like insights into how expensive these builds are going to be if we schedule them on one or the other. And so we'll make sure that we still execute all of our tests that only run on one architecture on that architecture, but everything that can run on either, we'll just schedule based off of machine availability. And we're still getting data into this, but it looks like most people don't really care where you qualify them, right? But you have some people that do. So with the configuration we have, you're saying that you can very easily opt out of like running your targets on one architecture or the other. But if you don't, then we are able to detect that, oh, these targets actually are compatible with both, and we'll just run them when they need to be run. The way this works with release is that release does what we call fill in the blanks testing, in that say we spread your targets across architectures and you have some level of coverage. We call this target comprehensive coverage. And release knows that, oh, hey, you're actually trying to deploy to an ARM machine. It'll look at everything that TAP ran and be like, okay, of 10 targets, TAP ran 6 on ARM, so we can just use those results right out of the bat. And now they only need to re-execute those 4 tests that were missing, which actually saves costs across the pipeline and guarantees a lot of coverage early on in the pipeline because, like you've said, post-submit testing runs much more frequently than releases, because typically releases happen, say, once a day, whereas like we test every hour and a half or 2 hours. And okay. And that essentially makes sure that devs get signal, because if things fail on one architecture, they likely will fail on other architectures. But the release pipeline still has to do very minimal testing before it can like get out of it. And so that's kind of the trade-off we're making. And now we're open for questions.
Okay. We have time for maybe one question.
Thank you very much.
Please come forward so you can speak into the microphone.
Here?
Yeah.
Hi, so it was very interesting. I have a quick question. So you said that you can run some of the projects on x86 and some on the ARM, right? So like the first question I have is there like anything like that's better than the other in terms of the cost and is in terms of how the process, like, or it just depends on the project?
Okay. So the question was for the audience, since she was facing this way, you might not have heard her, is there a difference in cost between running on x86 and ARM? And is that influencing your schedule? The answer is the cost difference is a complicated story. And it's different for the cost of compilation versus the cost of executing the test. And so we find that the test execution cost in terms of like the number of seconds it runs on the machine is pretty comparable. Like you're not going to see like massive differences in the total time it takes on the machines that we have right now. But right now the compilation costs can actually skew quite differently, because since most people are building for x86 most of the time right now on their local machines, because we're still like scaling out this project. It hasn't fully finished deploying everywhere. Because of the build caching effects in Bazel is much cheaper to compile usually for x86. So it's complicated, but we're trying to do some resource-aware scheduling to look at the resources. And I'm
It's
not
a time-based thing, because as like we have more machines in the fleet, then these caching costs start to change, and it will start to eventually become efficient to run all of our builds on ARM. We're just not there yet.
And then another quick question is that, so is there a way, like, because you said that some of the like projects are compatible only for the ARM. So is there a way to make those projects compatible for the x86 as well?
The question was you said some projects are only compatible for ARM. Can we make them compatible for x86? And I assume vice versa.
Yes.
So the main effort has been in the vice versa, making all of the projects compatible with ARM, because by default, none of them were. So nothing was running on ARM originally when this project started. And so there's been a lot of manual effort to like port everything to start running. So, but there's not that much that's on the other side. Okay. All right. So thank you, everybody. And yeah, it's fine. And you can feel free to ask me questions during lunch break. And I'm going to stop the recording and we'll go to the next presentation.